With no further ado, let me get to tonight's speaker. The nice theme we had this year was, I thought, well, let's feature our young astronomers. And so we've seen that. So all of our astronomers this year are kind of on the younger side, which is fun, they're exciting. And the nice thing about the young folks is they come and they bring a lot of energy. You fall in love with them and the exciting work they're doing. And then the bad thing is then they leave because they're usually only here for 3 years as postdocs. And that's the case with tonight's speaker, Jen Van Saters, who, good for her, but not so good for us. She's just gotten a faculty job at the University of Hawaii, which is really very exciting. So let's congratulate her on that. I don't know how many people actually have an understanding of just how hard it is to get a faculty job these days. A typical place like Hawaii probably gets 250 to 300 applications. And those are all PhDs, and they're all very good, and there's a lot of really great people. So when our people get jobs, we're really, really proud of them. And I think after tonight's talk, you'll see why she got this job. Jen's doing some really amazing work on stars, and that's not doing it justice. People were asking me today what the talk is about, and I say, it's on stars, and they're like, that's pretty general. I'll let her explain the details of exactly what this is. But to me, one thing I love about her work is that it also shows how a field evolves in time. Because when I arrived at Carnegie 23 years ago, and nobody was working on stars, it was just this thing, we had kind of done all the work we could do with stars with the technology and the resources we had at the time. And what you'll see tonight is that with new techniques and new technologies, we're really able to kind of understand these objects like we never have before. So with that, let me introduce tonight's speaker, Jennifer Van Saters. Come on, Jen.
Hi. So as John said, I am a postdoc at Carnegie Observatories, which means that for the last 3 years, I have had an unusual amount of freedom to sit and think about whatever it is I chose to think about in science. And so I spent most of my productive waking hours for the last 3 years thinking about stars, thinking about what goes on inside of a star, the kind of physics that is important for the interiors of stars, how stars evolve and change as a function of time, and how that evolution matters for planetary systems like our own. So this is one of those fields of astrophysics that's fairly easy to draw kind of real-life examples from, right? Because we live with a star. We have a star in our own backyard. It's the sun's radiation that's the thing that's responsible for helping to keep our planet warm enough that liquid water exists on the surface. Without liquid water, we don't have life as we know it. And when we think about energy in biological systems, biological systems of which we are a part, right? That energy, when you get down to it, comes from the sun. Plants photosynthesize. Those plants are eaten by animals. We eat those animals and plants. And so the kind of energy that moves through biological systems does in fact come from this star that sits in our neighborhood. And if you came here tonight driving a gas-powered vehicle, the gasoline in that vehicle is essentially stored starlight, right? This is fossils of plants that were gathering sunlight many millions of years ago. So there's lots of reasons to care about what the sun does because it does in fact influence our lives on a day-to-day basis. Now the sun's not only a benevolent neighbor. So this is an image, a movie actually, from the Solar Dynamics Observatory showing 3 solar flares. What you're seeing in the color here is ionized gas from the sun, and you can see it's kind of tracing out some loops in some regions. This is where that ionized gas is tracing the magnetic field of the sun. And near the surface of the sun, that magnetic field is kind of complicated and tangled. And what happens is occasionally you get a coil of this magnetic field that buoyantly rises to the surface, and when it does, it flings a whole bunch of material away from the star with it. And we call this a coronal mass ejection. Now, if we happen to be in the direction of a coronal mass ejection, it's not particularly fantastic for civilized life here. One thing is that, well, first off, our magnetic field protects us from the worst of it, Earth's magnetic field. A pretty thing that happens is you get northern and southern lights at latitudes that almost never see the northern and southern lights. But the bad things that happen are you get interruptions of telecommunications networks. It's bad news for our satellites, and it can take out entire power grids, and has in the past. And so there's a whole branch of astronomy dedicated to understanding this kind of space weather the geomagnetic storms that the sun is responsible for, and mitigating the effects of those storms when they do happen. Now, if we take a step back from our own experience with a star and think about how stars play a part in galaxies and the universe at large, they're actually incredibly important objects, both for what happens in the universe and for the way that we study it. So in the background of this image here, we have a galaxy, and that galaxy is composed of stars. And if we're interested in studying how that galaxy formed, when it formed, what its conditions are, we need something that we can see in order to study, right? And stars have the beautiful property that they're bright, and you can see them very far away. And so when we study galaxies, and that's all the pieces of galaxies, gas and dust and stars and the dark matter that dominates galaxies, what we use very often are stars to trace it. Stars are something we can see that allow us to understand the parts of the galaxy that we can't see. So if you look in this image in the background, you see that there's several different colors of stars here. There's these clumps of very bright blue stars in the outskirts of the galaxy, and these are young, massive, newly formed stellar populations. If you look closer to the center, you see that you have this kind of haze of yellow and red. These are older, more mature stellar populations, usually lower in mass. And those dark orangish regions that you see are actually dust lanes that are blocking starlight from the background. And so you start to see that these systems that are important in the universe, galaxies, are also composed of stars. And so studying the stars individually gets us something. And just to bring the whole thing full circle again and back to us here on Earth, there's this famous quote that we are made of star stuff, right? So most of the material that you are made out of, most of the material you interact with on a day-to-day basis, whether that's carbon or oxygen or nitrogen or any kind of metal, was either synthesized in the core of a star during its life or during the explosion that marked its death. And the small fraction of things that aren't made in those two processes generally are made in some other stellar-related process. So stars are responsible for enriching our universe and the elements that we are made out of. And so they have a very direct impact on all of the things that we have here. So because stars are so important and they have such a broad range of applications for study, we have been studying them for a very long time. The Mount Wilson Observatory, up on the hill here, on a clear day you can look up on the hill and you can see the domes of the telescopes peeking up over the ridge. That observatory was actually founded to study the sun by George Ellery Hale. So in this image here you have one of the solar domes shown on the left-hand side, and George Ellery Hale using one of these solar telescopes to observe the sun on the lower right. And the kinds of things that you could do with this solar telescope were look at things like this. So this is a spot on the sun. It's a sunspot. It is darker than the rest of the sun, and the Mount Wilson Observatory was the first time that observations were taken to show that that sunspot is actually a little bit cooler than the rest of the star. And it is, in fact, a region where you have very tightly packed magnetic fields. And interestingly enough, they were studying the sun at Mount Wilson, looking at this large group of sunspots at the same time that a very strong geomagnetic storm hit Earth. This was during wartime, and it interrupted communications across the globe, resulted in an aurora at very low latitudes. And so they were starting to draw the connection between these geomagnetic storms and these features that showed up on the surface of the sun. Now, to give you a more modern view of what the sun's magnetic field looks like, well, first to say that when observations at Mount Wilson were done, right, they found for the first time that you could say with certainty that there was magnetism on the sun. And that might sound like a fairly novel statement, but not as deep as it truly is when you think about it, because we had developed the theory of magnetism here on Earth, under the conditions that exist here on Earth. And the fact that in a system very, very far away, under conditions very, very different than what we have here, our theories and ideas about magnetism still held, tells us that we were actually finding a universal law of nature. And that in itself is an incredibly deep statement. So this image of the sun that you're seeing in the background is actually during a total solar eclipse. So the dark thing in the center is actually the moon. And if you look carefully, you can make out the lunar features. And it just so happens that the size of the sun on the sky and the size of the moon are about the same. And this is because the sun is very big, but very far away. The moon is smaller, but a whole lot closer. And it just so happens that they are almost equal in size, apparently. And so when you have a total solar eclipse, the moon very neatly blocks the entire disk of the sun, And when you're no longer blinded by that disk, you can study the very outer regions of the sun's wind and corona. And so what you're seeing here is material streaming away from the sun. You can see some faint loop structures. This is all interacting with the magnetic field of our star. Now, our star is the only place where we can make these kinds of observations. And that was part of the reason that Mount Wilson Observatory was founded, to do really detailed observations of the surface phenomena of the corona of the sun. One of the quotes from George Ellery Hale is that it cannot too often be repeated that the sun is the only star whose phenomena we can study in detail. Now, this was very true when he made this statement, and it remained true for many, many decades after that. And you could still argue that in some ways it's still true today. And part of the reason for this is that when we observe other stars, all we see is a point of light. Those stars are very, very far away. We don't have the power to resolve them into a disk. You can't study star spots in detail like you can for the sun, these things that are very distant. You can't make these magnificent images of their magnetic fields. All you have is a point of light. That point of light can be a different color, it can be a different brightness, but you don't have the same kind of depth and detail. Now, that doesn't mean we can't get anything out of it. So what I'm going to show you here is actually a video. And this is going to show you one of the techniques that we use, diagrams that we use, called the Hertzsprung-Russell diagram. So what they've done here is taken images from Hubble of what we call a globular cluster. It's a group of stars that were all born at the same time, out of the same cloud of material. They're all the same age, and they're very dense on the sky. So you can see in this cluster here that you have stars that are blue and red and yellow in color, spread out all over on the sky. Now, if instead of just looking at where they spatially are located, if we now sort them by their colors, you can see that you have a distribution of objects that sit here. And if instead of just looking at color, you also look at how bright any individual source is, you can make what we call a color magnitude diagram, where color is on the x-axis and magnitude is on the y-axis. And what you see is that stars do not populate this evenly. There's definite structure. They live in certain places. There's a relationship between the color of a star, the temperature of a star is what that's telling you, and how bright it is. And the fact that stars trace out a diagram like this is telling us something about the deep interiors and the physics that operates in the inside of stars. So we'll take it back to there. So even for the sun, though, we can't see the central engine. We can't see the thing that really makes the star, where it's burning fuel. We can't see any of the interior structure. The only thing we get to look at is the surface. And on that surface, there's many things to study, but the deep central engine is obscured. So what we can do is, with this information that we have from these other stars that are only points of light, but we know that they have these relationships between color and magnitude, and our own studies of the sun, and ideas about what kind of physics must be operating in the interiors of these things, we can piece together a picture of what the interior of a star like the sun must look like. So this is our model for the sun. Now, a star is an object that is always seeking balance. You have a lot of mass in one place, and that mass is self-gravitating, so gravity is crushing this star together. And as gravity crushes that star together, the material gets denser and hotter and at higher pressure. The density at the center of the sun is 100 grams per cubic centimeter, which is, a rock is 5 grams per cubic centimeter. It's very dense. The temperature is 16 billion degrees, right? It's very, very hot at the center of the sun. What happens at the very center is you are now hot enough that you start a fusion reaction. You burn hydrogen into helium, and that fusion reaction releases energy, and that energy pushes against the crushing force of gravity. And so a star is an object that is constantly balanced between gravity pushing it in and this energy generation pushing it out. Now, the entire interior of the sun is not burning. It's just the very central region that's the hottest. The region outside of the core is called the radiative zone. And the best way to think about the radiative zone is to imagine that you have a room that is jam-packed full of people, elbow to elbow. There's no room for anybody else there, but somebody decides to try to get another person in, and they shove them into that room with a certain amount of energy. Now, that person will hit somebody, who will hit somebody else, who hits somebody else, and so the energy that you injected into this scenario by pushing somebody in moves through the room, but the people don't move very much at all. And that's the same kind of situation that you have in the radiative zone of the sun. The material isn't moving around very much, but energy is still moving through it. Now, outside of that, you have the convection zone. And when I say the word convection, you might think of things like a convection oven, right, which does a nice job of evenly heating your food because it takes the air and it moves it around in bulk motions. And that's what goes on in the convection zone of the sun as well. You have bulk motions of material. Energy is transported by these motions. So you have hot material that rises buoyantly to the surface, cools, and then sinks back deep into the star. Now, that's what the sun looks like today. It's been stably burning hydrogen in its core for about 4.5 billion years. It will continue to do so for another 10, but it doesn't have, for another 5. It doesn't have an inexhaustible source of hydrogen fuel to go with. Eventually, the sun will run out of fuel in its core. And when that happens, a series of things begin to change. So once you can no longer burn anything in the center, you don't have that force to keep the sun in balance, and gravity begins to win again. Gravity crushes the core in, and now a region of hydrogen around that core that wasn't hot enough before to burn is ignited, because now it's brought to higher temperatures. And so you ignite a shell of hydrogen burning around this dead helium core. And while that's happening, the very outside envelope of the star puffs up. You get an object that gets very big, very puffy, very tenuous. You go from something the size of the sun to something roughly the size of the Earth's orbit. As you burn this hydrogen shell, it moves out in the star slowly, and it rains helium ash onto that dead core. And eventually that dead core in a star like the sun gets hot enough that it ignites helium now and burns helium into carbon. That ignition of helium is a flash. It's an explosive event. Everything is ignited at once. But by the time information about that so-called helium flash reaches the surface of the star, this very tenuous, puffy thing, it's essentially been muffled. And at the surface, the star doesn't appear to have had anything going on the inside. So this entire event in a star's lifetime is hidden deep in the core. It's something we cannot see at the surface. Now, once a star begins to stably burn hydrogen, you have a burning hydrogen core, a hydrogen shell. But the thing is, if you take two stars, one that has not yet ignited helium and one that has, they can look exactly the same on the surface. They can have the same color, the same temperature, the same brightness, and there's nothing that you can see from the surface of that star that tells you that one is burning helium and the other one isn't. And this is the frustrating thing that stellar physicists have had to deal with for 100 years, is that we have very strong predictions from physics and from the models that we build that these physical things must be going on. The structure of the star is changing dramatically, and yet we can't see it. It's all hidden in the deep interior. Now, another incredibly important observation that was done at Mount Wilson showed that the surface of the sun is actually very slowly pulsing on periods of about 5 minutes. And it turns out that this is the key to seeing inside of a star. And I will, in order to tell you how that works, let's come back to something a little more familiar. So, on Earth, we have earthquakes, in Southern California in particular. This is the San Andreas Fault, and what you're seeing here is two tectonic plates that are bumped up against each other. These tectonic plates are moving against each other, and they're not doing it particularly smoothly. So they stick, and then they release, and stick and release. And every time you get one of these quick releases, you inject a bunch of seismic energy into the planet. People nearby the earthquake, nearby that slip, feel it as the ground shaking, right? But even very far away, sensitive instruments, seismometers, can pick up the fact that this earthquake happened somewhere on the planet. Now, if you look at where earthquakes happen over the course of many decades, you can actually trace out quite beautifully the location of tectonic plate boundaries. And so what the game that seismologists play is they set up an array of seismographs all over the planet, and what you do is you wait for an earthquake to go off somewhere. That earthquake injects a bunch of energy, and then you wait at all those other seismographs, waiting for the waves, the energy from that earthquake, to arrive to you. So in this kind of schematic diagram here, we have kind of an onion layer schematic of Earth, and you have this focus of the earthquake up here. And you have this earthquake that goes off. That earthquake sends a bunch of seismic waves into the interior. And in this particular diagram, you can see that, depending on what path you take through what regions of the interior, that wave gets deflected and bumped around. It takes a different amount of time to move. And so to move through it. What you can imagine doing is setting up seismic stations all over here. You wait for an earthquake to go off. You ask, how long did it take that earthquake energy to reach me, and what kind of waves actually did? And if you're careful enough about it, you can do the inverse problem. You can say, I don't know anything about the inside, but I know when these waves arrived and how long it took. And you can invert the problem and figure out what the interior structure of the Earth is. And this is how we know that the Earth has a solid core, a liquid outer core, a mantle that's viscous, and the very stiff crust. It's from doing seismology on Earth. Now, in a star, you don't have tectonic plates. You don't have a solid surface at all. But what you do have is this convective envelope on the outside. And I said that this envelope is kind of a turbulent, churning place that's got lots of motion. That motion helps to continuously beat on the interior of the star. And what it essentially provides is the stellar equivalent of an earthquake. That star is set vibrating, ringing, by the motion of material in the convection zone. And that is what this is, right? This is the recognition that there's motion of the surface. I didn't explain this well before. So what you're seeing here is that the dark regions are regions of the sun that are moving away from you, and the light regions are regions that are moving towards you. Now, we cannot put a seismograph on the sun. First, because there's no solid surface, and second, because the surface of the sun is about 10,000 degrees Fahrenheit. Nothing would survive it. Right? So we need other ways of figuring out that these waves are present, and this is one of them, this kind of observation. So this gives birth to a field that we call asteroseismology, seismology of the stars. If it's for the sun, it's helioseismology, seismology of the sun. And a way to give you a kind of intuitive feeling for what it is that we're learning here is to make the analogy of a bunch of cowbells. So you would imagine if you had this collection of cowbells and you rung them all, set them all ringing, they would all have slightly different sounds. If you take a big cowbell and ring it, it has a very deep, low-frequency sound. A little cowbell will have a high-frequency sound associated with it. If you change the shape, if you change the material, you change the size, that all changes the way that that cowbell will sound. And the same is true of stars. If you take a very big star, that big star rings with a very low-frequency sound. A very small star rings with high frequencies. And if you start changing the interior structures of these stars, changing what they're made out of, changing how big they are, you will change the set of sounds that exist in them. And stars are a little bit like a musical instrument in that it's not a single frequency that they vibrate with. They have a set of vibrations, and that set of vibrations give the star a voice or a particular sound that you can associate with it. So this is the observation from Mount Wilson. This is a more modern version of it. This flickering that you're seeing is the typical 5-minute oscillation timescale of the sun. It's been sped up so that you can easily see it. But to give you an idea, the surface of the sun is moving about as fast as this guy. And that motion is about as big as this guy. Now, the fact that I can draw physical examples that you can understand, you know how fast a tortoise walks, and you know how big a whale is. The fact that you can viscerally understand those scales tells you that we might be doing something hard here. Because usually when we talk about scales in astronomy, they're things that are very difficult to imagine. I can tell you that the radius of the sun is 70 billion centimeters, but you can't really imagine what that is easily, right? You can't imagine a whale and a tortoise. So this observation actually tracks the motion of the sun. And we can do it for the sun more easily than other stars because the sun is close and bright, right? Anything you do first on the sun because it's the easiest place to see anything. Now, as you get this physical motion at the surface, what's happening is the material is getting compressed and rarefied, so it's getting hotter and cooler. And as that temperature changes, you get intensity variations. So the star actually changes in brightness and sits there and flickers on this 5-minute time scale that is typical for the sun. Now, this is not the kind of flickering that you see when you go outside at night and you look up into the sky. That's the atmosphere getting between you and that star and messing with the path of that light as it moves from the star to you. This flickering is far, far, far more subtle. So to give you an idea of how subtle it is, We'll draw another analogy. This is the Luxor Hotel in Las Vegas that has this spotlight on the top that they claim is the brightest spotlight in the world. It's actually a room of spotlights. And detecting these oscillations on a star like the sun is the equivalent of saying to your friend, I'm going to go stand in the middle of this room of spotlights with my cell phone, and I'm going to flick my cell phone flashlight on and off, point it up, and I want you to fly overhead, look down, and try to detect me flicking that flashlight on and off against the backdrop of this spotlight. So not super easy. And to give you a number to attach to it, it's a few part per million variation in the brightness of these stars. So although we first detected these oscillations in the sun on Mount Wilson in the 1960s, we really couldn't do much about it until very recently. It's just trying to detect these very slow, very small motions or these very subtle changes in the brightness of a star takes technology that we did not have at the time. But this field was cracked open by the Kepler satellite. So Kepler, which you might have heard of, was designed to search for Earth-like planets around sun-like stars. And it does that by staring, essentially unblinkingly, at a patch of sky for 4 years, taking data every minute or 30 minutes, and just waiting. Waiting and hoping that a planet will pass between you and a star, and as that planet passes in front, it blocks a tiny amount of light from that star. And so you see that star dim for a few hours and then get brighter again. And that's your signature of a planet. Now it turns out to detect an Earth-sized planet against a star that is the size of the sun, you need few part per million precision in your ability to measure the brightness of a star. And it turns out that while principally a mission to study exoplanets, Kepler was a fantastic machine for detecting these oscillations. So if you are familiar with the night sky, this field, all the results that I'm talking about here were actually done in a region of sky that's between the constellation Cygnus and the constellation Lyra. It's a 100 square degree patch of sky. And we were successful. We actually see the presence of these pulsations in these stars. This is a light curve, so it's tracking on the y-axis how bright a star is, and on the x-axis over time. So you're tracking this particular star for about a month and a half, and you're looking for variations in how bright it is. And that's not just noise that you're seeing, that's actually the presence of these oscillations in a star that's very similar to the sun. Now, if you look at other stars in Kepler, some big stars and small stars, you see that they look very different when you start looking at how they flicker. The large star here, shown with the cyan curve, shows you that these big stars are moving slowly, the pulsations are slow, and the amplitude of those pulsations is big. Now, if you look at the smallest star on this diagram, the white curve, you find that the star is pulsating faster, but it's also pulsating with a lower amplitude. And from this diagram here alone, you can very easily point to this star and say, that guy is big, and that guy is small. And that in itself is so much more than a point of light can easily give you, that it's an amazing advance forward. Now, when we actually work with this data, we don't work in this space. If you're familiar with what a Fourier transform is, we take a Fourier transform of this. If you're not familiar with what a Fourier transform is, it essentially allows you to pick out the typical frequencies at which this star is oscillating. And you can make a diagram that we call a power spectrum of what these typical frequencies are. And so this is for this star that I showed you earlier, that was very similar to the sun. And each of these peaks here represents a frequency that the star is pulsating at. And you can see that there's all kinds of structure and detail and order to this diagram. This thing represents this star's fingerprint, or you can think of it as an ultrasound. There's an amazing amount of information carried in this power spectrum. Just by looking at where it peaks and the kind of characteristic spacing between these different modes, I can tell you how massive that star is and how big it is. By looking in detail at spacings, much more subtle spacings between things, you can say what's going on in the deep core of this star. Those modes are actually moving through the deep interior of the star and tracking, essentially, how much hydrogen that star has burned to helium, which gives you a way of figuring out how old a star is. So I personally have spent a lot of time thinking about stellar ages, because when we study stars, it's very difficult in practice to determine an age. For the sun, we know the sun's age not because we study the sun, but because occasionally a very old piece of rock from the solar system that formed at around the same time as the sun falls to Earth. We date it in a lab with radioactive dating, and that's how we know how old the sun is, not from studying the sun itself. So when we do this for other stars, stars age exceptionally gracefully. Their surfaces just don't change very much. But if you have a tool that allows you to say this star has half of its fuel left, you have a way of figuring out how old it is. And ages are interesting across the board, right? If you're studying exoplanet stars, if you're studying a galaxy and the populations of stars there, knowing how old something is, how long ago it formed, is a very powerful piece of information. So we can answer the questions: how big, how massive, how old? Are my models right? Really in detail for the first time. Now, you'll remember this diagram, and you'll remember that I said that a star that's burning helium in the core with a hydrogen shell and a star that has a dead, inert helium core and a shell can look exactly the same at the surface. But now, if we're looking at them in these seismic oscillations, essentially with sound, those waves are moving through the entire interior of the star. And the interiors of these two stars are very, very different. So seismically, when you look at these two objects, they look very different. You can, by eye, just look at it and say, that one is burning helium and that one isn't. It is a very obvious difference between these two things. And so this is an example of a very strong prediction of stellar theory that we figured must be right, because it was such a basic and strong prediction for so long. But this is the first time that you actually got to observationally test whether or not this was happening. So this is an incredible advance in the way that we do things. This opens up entire new windows into the way that we study stars. It allows us to answer questions that have been lingering for a century. And it allows us to learn about the parameters of a star, its mass, its radius, and age, with a precision that's entirely unprecedented. And so this completely changes the game. This was a problem that was not worked on very much in the last couple of decades because we had, as John said, done what we could do. And then Kepler launches and the field is wide open again. So to finish the talk, I want to play something for you, which is the sound of the sun. Well, the sun's oscillations shifted up into the audible range. So you can hear what these pulsations, these sound waves in the sun, actually sound like. Oh, if I can get this to work. All right, and with that, I will take any questions. Things like neutron star mergers. So, to repeat the question, I mentioned that there were other stellar processes that were important for producing various elements. One of the things I was thinking of was neutron star mergers. So a neutron star is a remnant of a star. It's a dead stellar core. And when these things merge, it's thought that they produce a series of, of elements that don't generally get produced in the cores of stars as they burn.
You said that you can't really tell the difference when helium starts burning, but can you tell the difference when the star starts burning other elements?
Yeah, so the question was that we can't tell the difference between when helium exactly starts burning, but can we tell the difference when it starts burning other elements? And the answer is that if you wait long enough, you can tell the difference between a star that is burning helium and isn't, because it moves on the Hertzsprung-Russell diagram that I showed you. So if you wait long enough, that star begins to move to a different region. And so you are able to say that that thing must be burning helium. And the same is kind of true when you ignite other things. The star begins to move on that diagram. The statement that you can't tell the difference is that there is some period of time where those objects overlap on that diagram. They look exactly the same. And if you wait long enough, the difference becomes apparent, but you have to wait, is the problem.
You mentioned you do a lot with Kepler. Beyond Kepler, what instruments that are coming on the ground or in space are you looking forward to?
Yeah, so the question is, what instruments on the ground or in space beyond Kepler am I looking forward to? And the answer is there's a whole bunch of things that are coming online in the very near future that are exciting. There's another planet survey called TESS, which will be all sky, and it will have the same kind of capability to do asteroseismology while it searches for planets, and that comes online in early 2018. It gets launched. There's a ground-based network of telescopes who basically look to reproduce the kind of observations that were done at the Mount Wilson Observatory for stars other than the sun. That's already operating and has produced a handful of really nice examples. And then further in the future, there's some European missions that will be essentially a Kepler on steroids, much bigger field of view, more stars, longer mission, things like that.
In terms of what you've studied so far, is there anything about the internal physics different from what you see that was originally theorized?
Yeah, so the question is, in terms of what we studied so far, have we had any surprises? The basic answer is we were pretty much right, which is the boring answer too, right? You wanted to be wrong. We have most of our stellar models, particularly for stars like the sun, have performed exceptionally well against the test of asteroseismology. But there are a couple places where things are different. I can give you an example of something I have spent a lot of time thinking about. So there's this observation that stars are rotating, and as they age, that rotation rate slows. So as they get older, they spin more slowly. And it was thought that there was a very nice, smooth relationship between rotation period and age, and everything was good. And that slowing down with time is linked to the magnetic field of the sun, or a star. And using these astroseismic ages, which are more precise for a wider range of stars than any other ages available, we were able to show that, in fact, that spin down stops at around the sun's conditions now. So something is happening around the conditions the sun is at now that is changing our magnetic field for our sun. So that was a surprise. Another surprise is that there's certain giant stars, for example, that have, when you look at their power spectra, they have strange features. They're missing some of their modes that you would expect to be there. And people also here in Pasadena have shown that the reason that those modes are missing is that the star has a very strong magnetic field in its core. And what's essentially happening is that you have this energy that's coming in, it hits the magnetic field, and it essentially ends up in a kind of magnetic greenhouse. It gets stuck in there, and so it never makes it back out to the surface. And so it's surprises like that, things we never really thought we'd be able to measure. We never thought we'd be able to measure the magnetic field in a core of a giant star, that have really been the places where expectations were not met.
Can you use these techniques eventually to determine when a star will go nova?
Yeah, the question is, can you use these techniques to determine when a star will go nova? And people are very interested in doing this. At the very late stages of a star's lifetime, so a star that goes nova is an object that's much more massive than the sun. And it goes through many successive burning cycles. It looks like a layer cake by the time it's done. It burns, it does the hydrogen, it does helium, and then it proceeds on to a series of other cycles. But it eventually gets to the point where it has a core full of iron. And with a core full of iron, you can no longer smash two iron atoms together and get energy out of it. And so you're done. You have no energy generation mechanism left. And so that star collapses under its own gravity. The center of the star is stiff, and so the star collapses in and then bounces off and blows up in a supernova. The question of if we can use asteroseismology to figure out precisely when that happens is something we don't have. People are trying to work on it now. The problem is that as stars get to this very late stage of life, they get very, they're not stable and well-behaved like the sun. They're doing all kinds of nasty stuff. They're throwing off mass. Their pulsations are different and more complicated. It's not always as clear what's driving those pulsations. It's not necessarily this thick convective envelope. It can be burning processes, there's a whole bunch of things that can come into it. And so it's theoretically a very challenging problem, but people are very interested in trying to do it because seismology does give you this insight into the interior and would allow you to try to figure out, try to produce a physical model that works better than what we have for those very late stages.
I was fascinated by that image you showed in 1961 of Mount Wilson. You showed the portion of the sun that were retreating and those events. I just wonder what kind of an instrument was used to create that image.
Yes, the question is what kind of instrument was used to create this image? And this was done with a spectrograph. So what a spectrograph does is it takes the light from a star and it breaks it up into all its component pieces. So you can imagine it kind of like the way that a prism works. You take a prism, you look at the light from the sun, and it breaks it up into rainbow colors. Now, there are atoms floating around in the atmospheres of stars, and those atoms like to absorb energy at certain wavelengths of light. And every atom has a particular fingerprint, a particular series of absorption lines that dominate it. And what this image is here is an image of the calcium absorption line. And what you're doing is that calcium absorption line, if you're familiar with Doppler shifting, so a real-life example of Doppler shifting is if you stand still and you have a train go by you. You hear its high frequency as it's coming, and then as it's going, it's lower frequency. It changes the wavelength at which things happen. So as you have this motion on the surface of the sun, this calcium line is being Doppler shifted, blue and red, and that's what allows you to tell what the motion is. It's a bit of a more complicated technique than it's easy to explain super quickly.
Are the coronal ejections ever strong enough to leave a geologic record on Earth?
Yes, they are. You are getting to the edges of my knowledge about exactly what they do in the geologic record, but there are, there are people that make arguments about particularly large events that happened in the past based on geologic record, yeah.
Are your measurements so precise that we can actually make a fingerprint for each individual star, tell them apart?
Yeah, so the question is, are the measurements so precise that we can make a fingerprint for each individual star to tell them apart? And the answer to that is that we hope someday to be able to do it. For the moment, it takes this, this measurement is difficult to make. And so it's really only for the brightest stars that were in the Kepler field that we were able to make astroseismic measurements to begin with. Of the kind of 150,000 objects that Kepler tracked, about 500 of them have seismic detections. 500 stars like the sun have seismic detections. About something like 20,000 of the red giants have detections. So it's definitely not every star in the sky, not yet. But eventually, that's what we hope to be able to do, to use seismology in this kind of, for essentially every star on the sky. So you can point to a star and say, I want to know exactly how old that thing is, exactly how big it is, and exactly how massive it is.
If not, let's thank Jen again.
Thank you.
If you have more questions, I'm sure she'd be happy to answer them. I'll remind you that, although this is our last lecture, we do have an open house on October 15th this year.
Do you want?
Look out for that. And I was just saying, yes, you said. Our open house is October 15th this year. If you haven't been to our campus at Carnegie, we encourage you to come. And we look forward to seeing you all soon. Thank you.